Hello, this is Chapter 6, Circular Motion. We want to talk about things that rotate here, and I've got a circle that we can picture. The distance from the center of the circle to the edge is called the radius, r, radius of the circle. As the object rotates, it's going to move through some angle theta, and we've seen theta before, so that's good. The number that we haven't, the quantity here that we haven't seen before would be this arc length. And so as we think about the arc length, a little object, a point on our object, whatever, a little ant holding on to the edge here, the wheel, whatever it is, it's going to move some physical distance that we could measure in meters. And we refer to that distance as the arc length. An arc, of course, is part of a circular path, and so that would be the length that would travel right there. These three quantities, the radius and the angle of rotation and the arc length, are all tied together by this formula that you see here at the bottom. S equals r theta. The arc length, S, is equal to the radius times the angle, but only, and this is important here, if theta is measured in radians. So let's take a moment here, remind ourselves how radians work. Here's the unit circle that we know and love. We talk about angle starting here at 0, the positive x-axis, horizontal to the right, however you want to say that. But that would be 0 degrees. As we go all the way around the circle, we come back and it's 360 degrees right there. So we've seen that picture before. We do the exact same thing with radians. We would start right here at 0 radians, again positive to the right, positive x direction, whatever. When we go all the way around the circle, instead of 360 degrees, we say that's 2 pi radians, and that is the other way to measure angle, or one other way to measure the angle there. So we can get back and forth between degrees and radians using this as a conversion factor. And if we just pick one of these, let's say that we'll take the 60 degrees right here. 60 degrees, if I wanted to convert that to radians, then what I would do is put in a conversion factor right here. And of course, this is my conversion factor. All the way around the circle is 360 degrees. All the way around the circle is 2 pi radians. Those are the same, and just different units. So I would match up the units, 360 down here, for no other reason than that makes the degrees cancel out. The 2 pi radians would have to go up top like so, and then I could do that calculation. I could say 60 divided by 360 is 1 over 6, and that would leave me 2 pi over 6 radians, and 2 over 6 is 1/3. So 60 degrees becomes pi over 3 radians, and you'll see that here is the 60 degrees, and there's the pi over 3 radians that we have. Now we like to use the pi over 3 or the 2 pi or whatever. We like to leave it in terms of pi because pi is an irrational number. It never repeats, it never terminates, but it's exact, right? When we say pi, it's exactly pi. We could come in here and say, well, you know, pi is approximately equal to 3.14, so 2 pi would be approximately 6.28, and you know, get an approximate number. But if we leave the pi in there, then it's exactly the right number. That has a certain utility to it, so that's what we tend to do. If you don't need that much accuracy, then you could just on your calculator take 60 times 2 times pi divided by 360, and you'd get a number over here that would match up pretty close. Let's see what that would look like. Here is 60 times 2 times pi divided by 360, and that comes up 1.047 blah blah blah. All right, the more of those digits you write down, the more accurate it is. Of course, you'd want to consider significant digits and how accurately did we know that 60 degrees to begin with. But if we took pi over 3, then we'd get the same number to 10 decimal places or whatever, right? The calculator does a pretty good job of it, so that's probably good enough for everything that we do. But we can do those conversions and they work out fine. So I'm going to put here or 1.047 radians. And typically that would be plenty good for what we do. I could go the other way, just do the exact same thing. Let's say that I wanted to convert 0.7 radians to degrees. I could put in the conversion factor here, and this time I'd have to stack it the other way. I'd put 2 pi radians on the bottom such that the radians cancel out. The 360 would go up top, and I would need to be a little bit careful here because I've got 0.7 times 360, and then I'm dividing by two things. I'm dividing by 2. I'm also dividing by pi. You've seen that before, but just be careful with it. So it would look something like this: 0.7 times 360 divided by 2, also divided by pi. There's option A, and you get about 40 degrees. If you wanted to do it the other way, you could say 0.7 times 360 divided by parenthesis 2 times pi, and you'd get the same thing. So 40.1 degrees is what we'd expect to see there. And again, that's probably going to be plenty close enough for what we do. Okay? But I hope that reminds you about radians and how they work. Nothing fancy, just a different way to measure angles. It's kind of like I could measure the length of my desk in meters, or I could measure it in feet. It'd be the same length, right? Just different units. So it's a similar thing here. I'd like to tell you about angular velocity. This is very simple. Don't let it trip you up. It's the speed of rotation. It's how fast an object is rotating. Okay? It's very similar to linear velocity, the old kind of velocity we talked about in chapter 2, but here it's rotation, and everything that we want to think about is something moving around in a circle about a central axis. So if I draw a little picture here, this could be the axis of rotation, right? Everything's going to spin about that. And if I had some kind of object, maybe the Earth here, for example, say, right? So here's the Earth, and we've got some green continents. There's North America and South America, and over here's all this stuff and this stuff, and then we've got some nice blue water, right? Not bad, huh? That whole thing is going to turn. It's going to rotate on its axis, and every day it spins all the way around its axis. That's a rotation. We might want to know how fast it rotates. So all we have to do is this right here. And we refer to that as the angular velocity. The symbol for that is omega. That's the lowercase omega there from the Greek language. If I figure the angular velocity for the Earth, every day it moves through 360 degrees. It takes 24 hours to do that. And so 360 divided by 24 would be 15 degrees per hour. Every hour the Earth turns through 15 degrees. If I do it in radians, then it would move through 2 pi radians in 24 hours. And you could drill that down to seconds if you wanted to. But 2 pi divided by 24 works out to 0.262 radians per hour. Okay, so those would be perfectly good ways to say angular velocity. Our preferred units, of course, would be radians and seconds. Radians per second would be the very best way to do it, but these others are also measure the speed of rotation, so they're valid. There's another one here that you should probably know about: revolutions per minute or revolutions per day, or I'll put revolutions per minute. Sometimes we abbreviate that RPM, but whatever form you see it in, that would also be an angular velocity and would measure the speed of rotation. Engines rotate, right? The crank shaft goes around and pistons go up and down. The number of times per minute determines how much energy, how much work the engine can do for me. So RPMs measures how fast the engine's going around, or anything else that a drill motor or something. Right here I have an object that's moving in a circle. In this case I've got a little red car that starts off here, and as it moves through this circle you can see that the yellow vector indicating velocity is constantly changing, right? When the car is on the right, the velocity points up. A little bit later, the velocity points to the left, then the velocity points down, and then right. And it just repeatedly does that. That's a change in velocity. We call a change in velocity an angular acceleration. So right here, my car is accelerating. And what we say is that it accelerates toward the center. If you think about that velocity vector, if I don't change the velocity, the car will continue to go in a straight line and it will end up in the ditch up there somewhere. So what I need to do is to have an acceleration. I need to change its acceleration toward the center of the circle. I need to push that car to the left. And then when it's up here at the top, I need to push it down so that it follows this path and keep pushing it toward the center. At every point on the circle, I have to push the car toward the center of the circle if I want it to move in a circle. I do that by turning the steering wheel, and then the wheels of the car turn, and those turned front wheels have friction. They don't like to slide sideways, so they go around the curve unless you go too fast or the road conditions are too slippery. Okay, but that's a centripetal acceleration. Change of velocity toward the center. You can see the A sub c there, our symbol for centripetal acceleration, always points directly toward the center. Newton says that if I'm going to have an acceleration, I have to have a force in the same direction. So something has to push the car to the left toward the center to get it to accelerate toward the center. So we also talk about a centripetal force. The centripetal force is what pushes it toward the center. The centripetal acceleration is its change in velocity toward the center. But that's the operative word there, toward the center. And that's really, if you take apart the word centripetal, that's what it means. It's center pulling, center acting, toward the center. Okay? Got the two formulas here. The centripetal acceleration is v squared over r. And I'll make up a number here for you. Let's say that the speed of this car is 10 meters per second. And let's pretend that the radius of the curve here is 20 meters. So with those numbers, you can see that it's really easy to calculate the centripetal acceleration. I just go v squared. That would be 10 meters per second. Don't forget to square it, right? And then divide by the radius, 20 meters. So I'd have 100 meters squared over second squared divided by 20 meters. And 100 divided by 20 would be 5. This meter cancels out one of those. So I'd have 5 meters per second squared. It's the same units that we're used to seeing for acceleration. And so it should be. It is a change in velocity, even if the car is going 10 meters per second at every point on the curve. The direction certainly changes, and that's enough. If I want to calculate the centripetal force down here below, then I also need to know the mass of the car. If I were trying to turn a bicycle, that would take a little push. If I was trying to take a car, that's a pretty big push. If I wanted to turn a tractor trailer in a circle or a battleship in a circle or something, it's a much more massive object. I'm going to have to push on it much harder. So let's make up a number here. If the mass is 1,000 kilograms, then we could bring that down here, put it in for mass. The velocity is 10 meters per second. We could use the number that we have above, but I'll put it back in here. And this time out, I would have, we had 5 before. We certainly will again for the rest of it, but 1,000 times 5 would be 5,000 kilogram meter per second squared. And of course you recognize that as our old friend Newton's. Kilogram meter per second squared is a Newton. So I need a force of 5,000 newtons to push this car with a mass of 1,000 kilograms in a circle of 20 meters, in a circle of radius 20 meters. That's a pretty tight circle, right? So I'm going to have to push pretty hard on the car. Centripetal force is important for anything moving in a circle. If you see circular motion, I don't know what's up with my pen here, then you have to have F sub c. And all you need to do is to figure out where it's coming from. Okay? So hold on to that idea. Circular motion means there's a centripetal force acting somewhere. Figure out who's doing it. All right. Let's go back just a little bit here, and I'll put in a problem that we could think about here. Let's keep the car going in the circle here. If I had the little red car going in the circle, and we'll say this is our car here, and we'll put in the velocity vector this way. We know, of course, that we need to push toward the center of the circle with a centripetal force like that to get this thing to move in a circle of radius r. So that circular motion there, and our job again is to find out what's pushing on it, what's causing it to move toward the center of the circle. The circular motion here is due to friction. When we turn the front wheels of the car toward the center of the circle, they don't like to slide sideways. So that's going to roll the car around the circle, and that friction is what's pushing toward the center. Right here we could say circular motion due to friction. There's the centripetal force that I have to have. I'm getting that from, it is the frictional force. So I just want to set those equal to each other. F sub c is equal to F sub f. The frictional force gives me the centripetal force toward the center. It is the cause of the centripetal force. Centripetal force, again, mv squared over r. The frictional force from chapter 5 we saw was mu mg on a level surface with nothing pushing up or down. So I'll put that in here. The masses cancel out, of course, and you can see that I could solve this for v or r or even g if I needed to. Let's just make up a number here. Let's say the coefficient of friction is 1. That's kind of standard for rubber on asphalt, so it applies for a car. And I don't know, let's find the maximum velocity that a car could move through a circle equal to, the radius equal to 20 meters. Okay, if I solve that expression for v, then v would be equal to the square root of mu gr. I have all those numbers. Coefficient of friction is 1. G is 9.8 meters per second squared. R here is 20 meters. So we'll calculate that up real quick. I need to do the square root of 196 would be 14. Meters per second. The very fastest that I can go around that curve, if the coefficient of friction is 1, is 14 meters per second. If I go faster than that, then I won't have enough friction, and my car won't stay on the path here. It will drift off to the outside of the circle. And so anything moving in a circle, look for that. I see it moving in a circle. Where am I getting that from? Here's another example. Maybe I have a rock on a string, right? So I've got a piece of string, I tie a rock or some kind of object to it. I'm spinning this thing in a circle, and because I see it moving in a circle, I know it has to have centripetal force. And I say, where am I going to get a pull toward the middle? Where does this F sub C come from? Well, here it's the tension in the string, right? So the circular motion is due to friction. And so not friction, I'm sorry, tension. So we would write F sub C equals T. Well, maybe that tension comes, we could hold it in our hand and spin it and kind of pull toward the center at every little second. You know, when you move your hand in that circle, it kind of automatically does it. We don't really think about it. Or maybe the string goes down to some mass right here. And I've got a little tube or some kind of thing right here, and I'm holding that. And as I spin the mass in a circle, it is this tension that pulls, you know, this thing down. Now we know enough from chapter 4 how to find the tension in that system. I could analyze the forces down here on this, and of course I've got mg pulling down and I've got the tension pulling up. So if I sum the forces and set that equal to mass times acceleration, then I could have either way you want to call positive is fine. We'll call up positive. So this would be T minus mg equals mass times acceleration. If I'm just spinning this thing at the right speed, then this mass stays at the same place. It's not rising and it's not sinking. Therefore, the acceleration equals 0. All that equals 0, and the tension would be equal to that mass on the bottom. And so I could come in here and I could say, and I need some different symbols here. Let's call this a big M right here. I'll put some feet on it to differentiate between the little m that we already have. My big M is moving in a circle. That means I have to have a centripetal force, mv squared over r. I'm getting that from the tension, and the tension is actually the little mass hanging at the bottom times g, and I've got an expression. Okay? Anything moving in a circle, got to have a centripetal force. Where did it come from? Was it friction? Was it tension? Is there something else going on that would supply us with that? Here, of course, you could solve this really easily for the velocity, you know, and we could do something like that and find out how what speed I should spin that thing at if I want it to stay in a constant orbit there, a constant circle, something like that. Here's one more for you while we're at it. Sorry. Sometimes you'll see kind of a circular loop like that, right? There's a little toy loop here in the car, in the lab, where you take a little Hot Wheels car or something and you hold one end of the ramp up high enough and you drop the car from here, and when it comes around it makes it all the way around the loop. You probably have seen such a thing like that. Well, the car is moving in a circle, right? So at every point on that track I need something changing its velocity toward the center. When that's down here, then clearly it's the track that's pushing on it toward the center. And we could set up an equation and find out how hard the track has to push to make that happen. When I get up here at the top, though, this is kind of a critical point, because if I'm not going fast enough there at the top, the car is going to fall. So the trick to this little toy, this game, is to make sure that this end of the ramp is high enough up. You put it on your bed or a desk or something high enough, and when you drop the car, you want to see if you can make it go all the way around the loop without it falling. Okay? But it's moving in a circle, so I have to have circular motion. I get that from F sub C. And where am I getting that from? What's causing it to move in a circle? up here at the top, at that critical point, the force of gravity certainly works on it. F sub c equals mg. I have a downward force toward the center of the circle in gravity. So if I'm trying to find the minimum velocity that this thing has to have, then I could come in here and say F sub c, this centripetal force, is mv squared over r. The weight of the car is mg, and I could set those two equal to each other, indicating that the centripetal force that I have to move in a circle is due, at least at that very top point, to the weight. I cancel the masses like this, and I could solve that real handily for the velocity of the car. It's due to the radius. So let's say the radius of this is 0.2 meters, something like that. I'd come in here and say g is 9.8 meters per second squared. The radius is 0.2 meters, and we could find that number here, square root of 9.8 times 0.2 would be equal to 1.4. If my car is not moving at least 1.4 meters per second here at the bottom, then it will fall, and I won't make it around the circle. This is a minimum velocity to stay moving in a circle. I need to move at least that fast. Okay? But that's a pretty common pattern in this chapter. You got to have centripetal force. Where are you getting it from? Set the two equal to each other. Now, here's a interesting formula that doesn't seem like it fits in what we're doing, but it really does. The law of gravitation, Newton worked out that any two objects with masses exert a force on each other. That by virtue of mass, there's an attraction. This could be two hydrogen atoms. It could be a cardinal and a bird feeder. It could be a gorilla and a banana. It could be the sun and the earth. It could be the Milky Way galaxy and the Andromeda galaxy. It doesn't matter. If you have any two masses, then this is Newton's law for gravitation there. Cavendish came up with this value g, and that's a number that you should have. You may want to write this down somewhere. It's certainly in the book, though. G is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, so that does two things at once. First of all, it fixes all the units. You can see that down here on the bottom, I've got the radius of the circle squared, and here, when we say r, we're really talking about the distance between these two objects, between the gorilla and the banana. Okay, they're not orbiting each other, so it's kind of, sometimes people get confused and try to cut that number in half. You don't want to do that. It's just the distance between the two objects. And if we're thinking about the sun and the earth, it is the distance between the two objects, but it's also the radius of the circle. Okay, so just leave it like it is. Put the distance between them, everything will be fine. But that value g works out, and Cavendish measured that for us a long time ago. Mass of the first object, the mass of the second object, the distance between them, and we can calculate these things really easily. Let's do a gorilla and a banana here. Since we've got it up, I'm going to say that here's my banana. The mass of the banana is 1 kilogram. I think that's a big banana. But here's the gorilla. And it's got a much larger mass. Let's say it's 250 kilograms, something like that. Okay? And if I know that these things are a distance of 3 meters apart, there is a gravitational attraction. The gorilla is attracted to the banana not only because he wants to eat it, but because the gorilla warps space-time and the banana warps space-time, and they pull towards each other. The banana is pulled toward the gorilla is pulled toward the banana. Now with everyday objects like bananas and gorillas and cardinals and pencils and pens and stuff, it's a small force, and I'll show you why right here. The force of gravity we said was equal to G, first mass, second mass, divided by the distance between them squared. So when I put the numbers in here, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, that's G. Now I need the first mass, 250 kilograms. I need the second mass, 1 kilogram. And I divide by the distance between them squared. Then I'll get the amount of gravitational force between these two objects. And let's do that real quick here, 250 and 1. So I need to put in G, 6.67, E, negative 11. Need to put in the mass of the gorilla, mass of the banana, and then divide by the distance between them squared. And I get this little bitty number. It's little bitty because it's got that 10 to the negative 9 on it. But let's put that down for 1.9 times 10 to the negative 9 or something like that. On the units, you can see here that I've got a kilogram and a kilogram, which cancel the kilogram squared. Here's a meter, which gets squared, which cancels that meter squared. The only unit left is newtons, which makes sense because we were looking for a force, right? But that's what happens with a gorilla and a banana. 10 to the negative 9 newtons. That's what, a thousandth of a millionth of a newton. Okay, almost nothing. If you put the numbers for the sun and the earth in here, it's a much bigger number. Of course, here I'd have to go 6.67 E negative 11. The mass of the sun is 2 times 10 to the 30 kilograms, and the mass of the earth is 6 times 10 to the 24 kilograms, and then they're separated by 1.5 times 10 to the 11 meters, and that has to be squared. This is a pretty big number. All right, 6.67 E negative 11 times 2E30 times 6E24 divided by 1.5 E11 squared. That's 3.6 times 10 to the 22. That's a big number. Okay, but you'd have to have a pretty big number to push the Earth in a circle around the sun. And that's what we're talking about here. Here's the sun. Crummy picture. Of course, it's not any worse than the gorilla, is it? There's the path of the Earth around the sun. It's almost a perfect circle. Not quite, but almost. And the Earth is held in orbit by this gravity, by this 3.6 times 10 to the 22 newtons. I have to have that much force in order to keep the Earth from going in a straight line. I need F sub c to pull it toward the center and to make it go around that circle. If I don't have enough gravity, then the Earth flies off into cold, dark space out here. If I have too much gravity, Earth gets sucked into the sun. Either one of those is very bad, by the way. But that's why this formula is an important part of what we're doing here. The law of gravitation is important because gravitation is what causes things to move in circles. So I need the law of gravitation to help me figure that out. Let's do one here with the Earth and the sun. If I put the Earth here, the sun here, and the Earth here, and I'm thinking about that circular path around the sun, I need a centripetal force toward the center, and I'm getting that centripetal force from gravity, right? Circular motion due to gravity. So set those equal to each other. And when I do, this centripetal force is mv squared over r. Gravity is big G m1 m2 over r squared. Notice that this is m1, this is m2, right? And when we do the circular motion part, when we do centripetal force here, that is the moving object. So this really should be m2 right there. The m2s are going to cancel out. This r cancels one of the r's over here. I'm left with v squared. If I take the square root of both sides, it's pretty easy to work out the speed, the rotation, how fast we're moving around the sun here. All I have to do is the square root of g, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of the sun. Again, that was 2 times 10 to the 30 kilograms. And I divide by the distance, and the distance here, 1.5 times 10 to the 11 meters. And this will give me the speed of the Earth, how fast we're moving right now. I think this is a really neat number, so let's punch this up and see what we get here. The square root, 6.67 e negative 11 times 2 e30 divided by, what do we need, the radius of the Earth, 1.5, or the Earth's orbit, times 10 to the 11 meters. And there's the number, 29,822. And that is in meters. If you want to see where that comes from, it takes a little bit of doing, but right here, this kilogram cancels one of those kilograms. This meter would cancel one of those meters. So then underneath a radical, I'd have a Newton meter per kilogram. We need to take the Newton apart. A Newton is a kilogram meter per second squared times the meter that I had divided by the kilogram here, and the kilograms cancel, so I'd have the square root of meter squared over second squared, which would be meters per second. I lost the second here, sorry. Okay, so that's my speed in meters per second. We're not used to thinking about meters per second, so if you'll indulge me here for just a second, what I'd like to do is to convert that. There's something like 1,608 meters in a mile, and then there are 3,600 seconds in an hour. You can see the meters are canceled, the seconds will cancel, so I'll be in miles per hour here, which is a little more conventional. I think you should just know that how fast you're moving. So I'm going to take the number we just calculated, multiply by 3,600, divide by 1,608, and I'll have the speed of the Earth around the sun at all times. There's the number times 3,600 divided by 1,608, and lo and behold, we're moving 67,000 miles an hour right now, all the time. I think that's pretty neat. Okay. I have to. Again, if I go too slow, then Earth will be sucked into the sun. If I go too fast, I spin out of orbit and end up in cold, dark space, and we all freeze to death real quick. So we're in the perfect spot, right where we ought to be. There's a habitable zone, is what they call that, and there's a little region where, little region right here where we're able to survive, and it's pretty thin. It's thicker than that. Well, I mean, this is not to scale at all, but you know, there's a little window there that works, and we're right smack in the middle of that. It's nicely planned out, and if we go in or go out, that's a problem. Okay. Here's what we just talked about. I drew it out instead of doing it here, If planetary motion, we need to move in a circle, we need F sub c. Where am I getting that pull toward the center from? I'm getting it from the force of gravity. Set these two equal to each other, and you'll be fine. Solve for whatever's unknown. Kepler worked out some of these, and he actually used his equations to get back to Newton's equations, which is kind of a neat trick. His laws look like this. He had 3 of them also, kind of like Newton did. But Kepler's first law says that the orbit of each planet around the sun is an ellipse with the sun at one focus. So they've got the planet here, there's the sun right there. This is an ellipse, it's a flattened circle. And if you remember anything from trig or analytical geometry, we talked about ellipses and that. There is a major axis that runs through the middle. You should have 2 points that are called focus points. And it would look something like that. The orbit of each planet is an ellipse, so we've got that flattened circle. The sun is at one focus point. It would look something like that. Now, Pluto's orbit looks something like that. Ours is much more circular than that. There's a number called the eccentricity that measures how flattened it is, and our number is, I believe, 0.02. So our path is much more a perfect circle, and we don't stray out as far from circular as Pluto. Halley's Comet, for example, has a very flattened circle like the one that you see in the gray box. And so some things have very flat circles, flat ellipses, and the other ellipses are almost perfect circles. So it just depends. But they're all ellipses. Okay? The sun is always at a focus point. That's the first law. Second law says, and this one is incredible considering he calculated this 400 years ago before they even had paper at the Walmart, Each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal times. This is the important part, equal areas in equal times. All right. So what they've done here is they said, in December, if I draw a line from Earth to the sun, it would be right there. And again, this is exaggerated just to show the flattened circle idea. But this would work for anything going around the sun or around any planet, the moon going around the Earth or International Space Station or whatever. If I draw a line at one time and at another time, then I could shade all this region in between those two lines. And Kepler worked out here that if you do that at the same time interval, over here I could go from June to July, right? And assuming that that's the same number of days, hours, minutes, seconds, whatever, then these two would have exactly the same area if you calculated them. And that's an astounding thing. The implication of that is that we're not always traveling the same speed. You can see that if the sun is here, then in this picture at least, whatever planet this is closer to the sun in December, and it makes this big long arc. It covers a lot of distance in 1 month, so it's moving really fast. It's got a high velocity over here when we're close. That's because the gravity of the sun pulls it in. It accelerates it, makes it go faster and faster. And then as the planet starts to move away from the sun, get farther and farther, the sun's gravity is pulling that planet back. It's slowing it down, and we cover a very small arc right there. So we have a low velocity. To me, this is an awful lot like riding your bicycle on hills. If I had a hill that did like this, when I'm up here at the top of the hill, I'm moving very slow. Gravity is accelerating me down, and so when I get close to the bottom, I'm moving very fast, and then as I go back up the hill, gravity is pulling me backwards, slowing me down again. And it's the same kind of potential energy well here that you have with the sun and the planet. So that's Kepler's second law. Kind of neat thing. I don't know of anything we would do with it right off the bat, but it's a neat thing. Here's the third one, and this one is kind of useful when we think about the solar system and other things in the solar system. Kepler's third law says that if I take the orbital period and call that t, and if I take the average radius of the orbit and call that r, if I take t squared over r cubed, I always get the same number for everything that's going around a certain body. The body could be the sun, and so I could look and say, here's Mercury, and here's Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune and Pluto, and you can see how as the orbital period increases, this would be t squared. Then right here I have the cube of the semi-major axis, then this goes up, and those have a constant value. There's a constant slope there. As I take t squared over, I'm sorry, I wrote that wrong. This should be r cubed. T squared over r cubed, then I should always get the same slope for that, a constant k. The easiest way to do that is in years of time. If I use time in years, and I do the average radius in a unit called AU, which stands for astronomical unit. That's the distance from the Earth to the Sun. Then these are really easy to work out this way, because when I do this thing, then the time for Earth, the period would be 1 year. It takes us 1 year to go around the sun, and r would be 1 AU. And so you can see that if I take t squared over r cubed, then that would be 1 squared over 1 cubed would be 1. So Earth's number, using years and astronomical units, is 1. What Kepler's third law says is that Jupiter's number has to be 1, and Pluto's number has to be 1, and the rocks in the meteorite and the asteroid belt has to be 1, and every little object. And so that's kind of nice whenever we find a new planet, right? When we find Makemake out here past Pluto, or if we find Eris, in between Mars and Jupiter, and all the dwarf planets that we found in the last 15, 20 years, they have to have that same number. So we can use that one of two different ways. If we can estimate the distance to that new planet, then we can get a really good feel for the time of how long it's going to take to orbit. Or the other way, if we could measure and say it moved from here to there in a certain amount of time and work out how long it's going to take to finish that orbit, then we can determine the radius of the orbit. So that's Kepler's third law. Those are in the book with some more examples and problems. Probably not on the test, but they are kind of neat. They do apply to circular motion and to gravitation, so I wanted to mention them here. And thank you for listening.